Hello and welcome. My name is Dr. Mark Taylor, and this is Delaware Tech Physics 111, Lesson 5, the second lesson of Unit 2 on forces and energy. So this one is Forces Part 2. And here we're going to talk about a number of very specific types of forces. Gravitational force, which essentially, when gravitational force is near the Earth, we just call that weight. The normal force, which you probably never heard of. Frictional force, which is the same as friction. Tension force, which is force along a rope or a cord or a cable, something that's pulled tight. Applied force just means a push or pull that somebody applies to an object, and some other forces. And then we'll give a brief summary of forces so you have it all together. Then we'll talk about a concept of balanced versus unbalanced forces. We've talked briefly about net forces. When the net force is zero, that means the forces are balanced. So if the net force is not zero, the forces are unbalanced. Then we'll cover something I like to call the 5 things all or nothing test. And we've actually done this in Lesson 4. I just didn't point it out as being the 5 things. Then we're going to discuss a method of analyzing force problems called free body diagrams. FBDs for short, and we're going to use the example of a hockey puck, of an air hockey puck table, and various examples of that. Then we're going to talk about how to use free body diagrams and force formulas to actually solve these force problems. So we'll go over some force formulas, we'll go over some important hints from the free body diagram calculations, and then we'll actually do examples of force problems where the motion ends up being horizontal, and we'll do some problems, force problems where the motion ends up being in a vertical direction. And then we have a number of advanced topics. Anytime you see advanced topics, these are there for your own education, your own interest, but you are not responsible for them on the exam. So I'm only going to briefly touch on these, but the answer key includes the answers to everything in this lesson. Okay, so there are many types of specific forces. And the first and probably the most important for you to understand is the gravitational force, which we abbreviate as F sub G, force sub gravitational. And when this force is on an object that happens to be on the Earth or close to the Earth, we just call that force weight. It's essentially the same term. When the object moves further away, we can't really use this formula. This is more of a simplified formula that you see below here. F sub G equals M times G. That's the mass of an object times the little g, gravity, that you're used to using. So we're going to talk about 2 types of things when we say gravity. We're going to talk about the force due to gravity, that's gravitational force, usually called weight. And we're going to talk about the acceleration due to gravity, which is what we used in the previous unit. The acceleration due to gravity is little g, that's the 9.8 meters per second squared. Now your immediate reaction might be, well, wait a minute, we learned it as negative 9.8 meters per second squared. Yes, you did. That's because we assigned a direction right away. But when you're doing force problems, I strongly recommend you do your calculations first and then ask yourself, what's the direction of the force that I just calculated? Is it up, down, to the right, to the left, some other direction? And then assign a positive or negative sign to it. Believe me, this will make things much easier for you when you do your final calculations. So we're going to leave the negative sign out until the end. All right, so the force of gravity is equal to the mass of an object, and that's in kilograms, times the acceleration due to gravity, that's 9.8 meters per second squared. So if you're given a mass in kilograms, just automatically, without even thinking, calculate the weight or the gravitational force from that mass. And you can do that quickly by just multiplying the mass in kilograms times 9.8. And you see in this example, 50 kilograms of of mass is equivalent to 490 newtons of weight. Weight is a type of force, of gravitational force. And because all gravitational force points towards the center of the earth, or if you're standing on the ground, it points straight down. So just get used to drawing your arrow to represent gravitational force or weight as an arrow pointing straight down. And that will tell you your direction for the weight. Now, so scrolling down a little bit, it says important, please do not confuse. Okay, so it's very important you don't confuse the force due to gravity, which is essentially the weight when you're close to Earth, and gravity as in the acceleration due to gravity. So weight is just m times g. And as I mentioned before, if you see a mass, and how do you know it's a mass? It's in kilograms. Kilograms is the unit of mass. If you see a mass, calculate the weight. You might not use it, but you probably will. And if you see a weight, calculate the mass by just dividing by 9.8 meters per second squared. The weight is a type of force. All forces are going to be in newtons, and mass is always in kilograms. The direction of the force is always straight down towards the center of the earth, or whatever other heavenly body you happen to be on. If you're talking about the weight on the moon or on another planet, it's the same thing, but you use a different g in that case. Mass is not going to change on the moon, but the gravity does. The little g gravity does. And that's why your weight is lower on the moon. Your mass is exactly the same. All right. So on Earth, the acceleration due to gravity is 9.8 meters per second squared, negative. But if in this unit, it's better to think of it as 9.8 meters per second squared in the downward direction. So because force of gravity causes acceleration due to gravity, both of those are in the same direction. All right. So some examples of calculations, and these are really things I want you to get in the habit of. If you see a mass, calculate the weight. If you see a weight, calculate the mass. So here are two examples. It says, what is the weight of an 84 kilogram object? Well, the second you see kilograms, that's the mass. And the weight is just equal to m times g. 84 kilograms, that's your mass. We always use kilograms in physics as a unit of mass, times 9.8 meters per second squared. That's our g. We'll worry about direction later. And when we multiply this out, use a calculator, obviously, you get 823.2 kilograms times meters per second squared. But we know from the definition of Newton that that is just a Newton. So instead of keeping track of your units, just remember, I'm calculating a type of force, specifically weight. All forces are measured in newtons. All masses are measured in kilograms. Acceleration is measured in meter per second squared. The second problem, you're given a number of newtons. Okay, so if they're saying this is a 950 Newton object, they're referring to a force, specifically the weight force. So they're telling you the force is equal to 950 newtons. Well, we use the same formula. We plug in the numbers that we know. We write 950 newtons for our weight, our F sub g. We don't know our mass, but we do know acceleration due to gravity is 9.8 meters per second squared. So our mass is equal to 950 newtons divided by 9.8 meters per second squared. Write that a little better. And again, plug that into a calculator, and you will get a value of 96.9 kilograms. Because it's a mass, it's going to be in kilograms. And there's our answer to that. It's the answer to the previous question. All right, let's look at the next type of force that we're going to talk about here. This is called the normal force, and we're going to abbreviate this as F sub n, a uppercase N. In many textbooks, you'll see this abbreviated as just a capital N. I'm going to try to avoid that. I want to make all the forces F sub something, so you always know they're forces. And because we already use N as the unit of forces, Newton, I think it'd be confusing if we called the normal force capital N. So we're going to call the normal force F sub n. What is the normal force? A force that acts perpendicularly from the surface, really up from the surface, on an object that's on the surface. Okay, what does that even mean? Well, let's back up a little bit. Let's imagine you're standing on the floor or the ground, and your weight is the force of the earth on you. It's the force of the earth pulling you straight down. That is your weight force, F sub g, and we can calculate that by taking your mass and multiplying it by g if you're on the earth. Okay, and that force is a force by the earth on you. We only care about what's on you right now. Now, if that was the only force on you, that would be the net force. And if that was the net force, you would start accelerating literally towards the center of the earth. So there must be some other force that's preventing it, some other force that's balancing your weight force. And in fact, there is another force. It's called the normal force. And you might say, well, where does this thing come from? Well, where it comes from is the molecules in the floor or the ground that you're standing on. Those molecules get compressed because of your weight on them, and they spring back. The molecules don't like being compressed, and they literally push back up. So that push back up from the ground is referred to as the normal force. Now you might say, well, why in the world is it called the normal force? How in the world is that normal? Well, this comes from the fact that mathematicians like to say, okay, if we have some line and we make another line perpendicular to it, let's say we make that arrow perpendicular to the first line, they have a name for any line that's perpendicular to a surface. They call it the normal. So the normal force happens to be a force that's pointing up from the ground. And while you can draw it the way I have here, a lot of times people will say, okay, here's some object on the ground. It has a weight force pointing down. And then they'll say there's a normal force pointing up. Well, just because my arrow starts in the middle of the box, it just means that's the force on the box or on the person or on whatever object is on the ground or the floor or a table. But the fact is, it's the floor that's the source of that. So if you wanted to be more accurate, you could write that is that arrow and then write this is this arrow, but that gets unwieldy. So we usually just start from the center of our box and say there's a force pointing down, that's the weight, and there's a force pointing up, that's the normal, and that force is coming from the floor. But both forces are acting on the box, and in this case, both forces are acting on the little girl here. All right, so erase some of this, leave the force normal there. So the normal force is a support force. There are a number of different forces we call support force. This is a support force because it's the ground supporting us. Otherwise, we would just start accelerating faster and faster until we reach the center of the earth. And that obviously doesn't happen. So this is the force that stops us from going through the floor. It's the force that stops any object from going through the ground. It's the force that stops your books from going through your table. The molecules in the table are pushing back up. Now you might say, well, wait a minute, I have different size things on the floor or on the table. How is the normal force dealing with that? Well, the normal force will grow and grow to match whatever the weight force is up until a limit. So if you have a small weight on a table, it's going to have a small gravitational force. The molecules are only pressing back a little bit. But if you had a big object on the ground, there's a huge weight force, and therefore they're compressing these molecules a lot. And now these things are pushing back up with a bigger force, and these two forces match. Eventually, if you put a big enough object, let's say you put a 10-ton chunk of marble in your kitchen, your kitchen's probably not going to hold up that 10-ton block of marble, and the kitchen floor will break, and the marble will go through the floor. Eventually, it'll hit the ground, and the ground will have enough normal force to stop it. But every surface eventually has a limit. So the normal force grows to match the weight force, but it's perpendicular to the floor. So if the floor is flat, and most floors are flat, the normal force will be straight up from it, perpendicular to that surface. Now you might say, well, what about if it's not perpendicular? Well, I mean, if it's not a flat floor. Well, that's beyond what we discuss in this course, but you'll see I actually have examples on the very next page. All right, so looking here, we see the normal force stops an object from penetrating the floor. Okay, that is the result of the normal force. It's a support force. All right, so here are some examples of normal force in action, and there is no one formula for how to calculate the normal force. It's going to vary depending on the situation. If you just have an object on a flat floor or a flat table or a flat ground, the normal force is really easy to calculate. You just figure out what the weight force is, and the normal force will be exactly the same magnitude, the same size force. It'll just be pointing up. So we'll say our gravitational force is in the negative direction. Our normal force will be in the positive direction. So the first question says, what is the normal force acting on a 10-kilogram box? Well, if the mass is 10 kilograms, remember, if you see kilograms, that's a mass, not a force, not a weight, a mass. Kilograms is always mass. So if you look at the hints, it says, are the vertical forces on the box balanced? Well, is the box going anywhere? Is it accelerating up in the air? Is it accelerating down towards the center of the earth? No, it's sitting right there. It's not moving vertically at all. And therefore, we know the weight force must be equal to the normal force, or at least the size of the weight force, we use absolute value, equals the size of the normal force. Really, one's the negative of the other. Well, what's the weight force? Well, it's 10 kilograms times gravity, m times g. So 10 kilograms times 9.8 meters per second squared. Our answer is going to be in newtons. 10 times 9.8 is 98 newtons. That's our weight. And if we want to be specific with our signs, we can just remind ourselves in parentheses that's a negative force. It's pointing downward. Are the forces balanced? Yes, they are balanced. That tells us two forces are equal. Therefore, the normal force must be positive 98 newtons. It's pointing up with exactly the same magnitude force to counter the weight of the weight of the box. Example 2, we have something slightly different. We have that 10 kilogram box with its weight of 98 newtons, but we're also pushing down with an additional 10 newtons of force. So they're 98 newtons down. That's our gravity force, gravitational force, our weight, 98 newtons in the negative direction. I'll write the negative over here in parentheses to remind you. This push is 10 newtons, also in the negative direction. So the normal force has to balance both of those. We know the box isn't going through the ground. I'm not pushing the box so hard it breaks the floor or the table that it's sitting on. So that means the normal force has to balance both the weight force pushing down and the push force pushing down. And therefore, if we add those two downward forces, our two downward forces equals negative 108 newtons. 108 newtons. And therefore, our normal force must be a positive, and I'll put that in parentheses, 108 newtons pushing back. It has to fight both the weight and the push force. Now, if we look at the third example is the opposite. Now, the push is up. It's helping the normal force fight gravity, right? The gravitational force is still the same. Nothing changes there. Force of gravity is still 98 newtons in the downward direction. We'll remind ourselves that's negative. And now we have a push up, and I'll just write the arrow to the side because we're running out of room. We have this push force of 10 newtons, but that's in the positive direction. And we have an upward normal force. This was a normal force also here. All right. So the normal force now has to balance the weight force, but not all the weight force, because some of it is helped by this 10 newtons. So instead of having to fight 98 newtons upward force, it's actually only having to fight 88 newtons of downward force. It's only having to fight 88 newtons in the downward direction. How do we know that? Well, if we add these two forces that we know together, we have negative 98 newtons plus a positive 10 newtons. That's what we know we have. That's negative 88 newtons. So our net force for just the two, it's not the full net because we haven't added in the normal force yet. But we know that when we add the normal force to the other two forces, we have to end up with zero force because the box isn't accelerating. And therefore, the only way for that to happen is for the normal force to be a matching positive 88, our normal force. Now, I do want to point something out here with these calculations. You can either assign everything a positive, negative number, and if you add up each of the forces, you should end up with zero net force for this box, no matter what the situation is. That's one way to do it, and that's what I did here. But another way to do it would be to say all the up forces must equal all the down forces, and that's actually the way I describe it in the answer key. So I'm giving you both ways of thinking about it. You pick the way that works best for you. All right, so I did tell you that normal forces are perpendicular from the surface, but the surface doesn't have to be level. It doesn't have to be a horizontal force. We just finished examples where it is a horizontal force, and these and all the problems you're going to get on the exam are going to be horizontal surfaces. But I want you to understand that while the force due to gravity, that is the weight force, it always points straight down. There's no getting around that. But the normal force is pointing straight up from the surface. So it's always perpendicular from the surface, hence the term normal force. It is always a normal line perpendicular to whatever surface. So as you can see, it changes its angle depending on how steep or shallow your floor is or your table, all right? And in these cases, we'd have to use trigonometry to actually do calculations. We're not going to do that in this class, so you don't need to worry about it. So let's look at the next force. The next force is the frictional force. Sometimes it's just called friction. In everyday English, we tend to call it friction. But friction is actually a type of force. We abbreviate it as F sub little f, lowercase f, or just with a lowercase f. In this class, we'll usually abbreviate it with a capital F with a lowercase f subscript, all right? And for the force that prevents sliding of one object on another is what we call friction. So when you're sliding a box on the floor, or a bottle on the ground, or a brick on another brick, all of those will result in some form of friction. And friction comes in two basic types. We're not going to go too much in detail in this course about the two types, but the two types are called static friction and kinetic friction. So static friction is the friction that keeps an object from moving at all. So you imagine if you've got a refrigerator sitting on your kitchen floor and you need to push the refrigerator, the static friction is what keeps you from even getting started in moving that refrigerator. But once you're moving, you'll notice it's slightly easier to keep that refrigerator going on the floor once it's already moving. That friction is called kinetic friction. Kinetic meaning moving friction. Static meaning standing still friction. And these frictions, they're different types, but they basically result from the objects on a microscopic scale. If you look at them, you've got one surface sitting on another. And no matter how smooth an object appears to be, and no matter how smooth the bottom object that it's sliding on appears to be, if you have a good enough microscope, eventually you'll see little bumps and ridges in the surfaces. And these bumps and ridges get caught within each other, and that's what causes the friction. As you're pushing side to side, the weight of the top object is pushing down, and the normal force from the bottom object is pushing up, and as a result, it makes it hard to move sideways in this. Now, friction will always be in the direction opposite the direction you're trying to move. So if you're trying to push to the right, if you're applying a force to the right, that's what I've got, this applied force here, the friction will always be to the left. It's always in the opposite direction of movement or attempted movement. And we have a way of calculating friction, and this is a formula you're going to see over and over again. This is the force of friction equals a constant we call mu. So we actually use the Greek letter mu. I believe if we were Greek, we would call that me, but we're going to call that mu. That's the English pronunciation of that Greek letter. Mu is the Greek letter for m, essentially. It's the lowercase m. And it's just a constant. It doesn't even have a unit. It's just it's what we call the coefficient of friction. And that coefficient, mu, has to be multiplied by the normal force. So the normal force is this force from the bottom surface pointing up into the top surface. So you can think of mu as a fraction that tells you what fraction of the normal force will be turned into frictional force. Because mu is a number that's usually between 0 and 1. In other words, it's a very small number. You can think of it as a percent, but we don't write it as percent, we write it as decimal. But so between a typical box on the floor and the floor, you might have a mu of 0.2. That means 20% of the normal force will be converted to create a frictional force. The normal force doesn't go away. It's just frictional force is created as a result of the normal force and the coefficient. And you might say, well, where's the coefficient come from? Well, the coefficient is different for every pair of objects. So the values, as I mentioned, go from 0 to 1 usually. Rarely they'll go above 1. But a value close to 0 means the two objects are really slippery on each other. There's almost no friction. And a value of 1 means there's an enormous amount of friction between the two. So ice might have a frictional coefficient of only 0.01, which is like 1%, meaning very little will be turned into friction when it's ice on ice. That's why ice is so slippery. It has very little friction. No matter how much weight is being put on the ice and how much normal force is pushing back up, you don't get much. So But other things like sandpaper on sandpaper have very high coefficients of friction. So all of that normal force, or most of that normal force, will result in a very high frictional force. So we use this formula. It's just three things. So if you don't know the frictional force, you can calculate it if you know nu and you know the normal force. And we just finished explaining how to get the normal force. So typically what you're going to find in problems is somebody's going to give you a mass. You're going to know little g. You'll use that to get the weight force. The weight force will tell you something about the normal force. And if you have mu, you can calculate the frictional force. So with just three things, you can get the values for those three forces. So it's always good to keep your eye out for those things in a test problem. Sometimes they might give you the frictional force and you'll be asked to calculate mu instead. So it's a great little formula. Frictional force equals mu times the normal force. All right. Now you'll notice in this diagram here, and I'm going to erase a lot of these pieces so that we have a clear view of what's on the screen. If you look at this diagram, we have all these force arrows, these vector arrows representing the different forces. We have a weight force so we're talking about the forces on the top object here. Okay. We have its weight, so Earth is pulling it down. We have the normal force. This is the bottom surface pushing back up on the top surface. Somebody is pulling this object across the ground, and as a result, we end up with friction pointing in the opposite direction. Well, if you want to simplify this, you don't have to draw these pretty pictures of one set of material over another with all the bumps and grooves. All you have to do is draw the top thing, the one thing that we're looking at forces on, and literally draw it like a dot. No cartoon skill necessary. And then you just say, what are the forces on it? Oh, well, I have the weight force pointing down, the normal force pointing up. The applied force in this case is to the right, and therefore I'll probably get some friction to the left. And that's this diagram with these different forces is referred to as a free body diagram. We treat this object as the only object in the universe. It's free body. It's a body that's free from everything else. We didn't write the bottom surface. We didn't write the person pulling on the top surface. We just wrote the object that's being considered that has all the forces on it, and we just write it as a dot to keep it simple. And so that's the free body. It's free from everything else, and it's just a diagram with forces on it. So this is a free body diagram. And this is very typical of the free body diagrams you're going to be writing. And you'll notice in this particular case, because the applied force is to the right, we'll call that a positive. Because the resultant friction is to the left, we call that negative. Gravity is pointing down, that's a negative direction. And the normal force is pointing up, that's a positive direction. So do your calculations and then assign positive and negative signs to tell you the direction of each force. All right. Now you'll notice to get the force, the normal force in a flat ground, and all of your examples are flat ground, is frequently going to be the same as the gravitational force, the weight. Well, that's just mg, so you can quickly calculate it this way. I would recommend calculating things one at a time. Use the mass to calculate the weight. Use the weight to figure out what the normal force is. Use the normal force to figure out what the frictional force is. It's that one there. All right, get in the habit of doing that. Believe me, it'll make your life a lot easier. All right. So looking at some of these notes here about the coefficient of friction. So it's a specific constant between each pair of surfaces that rub together. So there are actually tables. You can go online and find tables for both the static version of the friction and the kinetic version. In other words, the coefficient for when you're just starting to make something move or when it's already moving, that's the kinetic friction. So there are always going to be two different coefficients for each pair of surfaces. Oh, I'm looking at ice on ice. I'm looking at steel on wood. I'm looking at rubber on a cardboard. And you can find these tables with all these different pairs of materials and get these values. But we're going to give you the values, or we're going to ask you to calculate them from values you already have. You don't have to look up anything. But those coefficients tell you how slippery things are. Numbers close to zero, coefficients close to zero, are super, super slippery, infinitely slippery, whereas close to 1 or even higher than 1 are incredibly rough surfaces. All right. Now, the coefficient is a ratio. How do I know it's a ratio? Because look at the formula I gave you. It's the friction force equals the coefficient times the normal force. Well, if I rearrange this, it's the coefficient is equal to the frictional force over the normal force. It's the ratio of those two. They are both in newtons, and newtons divided by newtons cancel out. So the coefficients of friction have no units. It's one of the few things you're going to see this semester that doesn't have a unit at all. So your answers, your coefficients might be 0.27, 0.31, 0.05, all right? But there's no unit, okay? And like I said, you're going to get 2. We'll tell you a coefficient of friction. If we don't say anything, you don't have to worry about it. And we're not going to make a distinction that you need to keep track of in exam questions, not in this course. All right, so a couple quick problems here. What is the frictional force if the normal force is 450 newtons and the coefficient of friction is 0.19? Well, force of friction equals mu, the coefficient of friction, times the normal force. Well, we just multiply them together. 0.19 times 450 newtons. And you'll notice the only unit in this problem, the only unit at all, is the newtons. Well, we plug this into a calculator, and we find out that the frictional force is 85.5 newtons. It's generally going to be significantly less than the original normal force, and it is. It is 19% of the normal force, which is 85.5 newtons. All right, second problem. If the normal force is 320 newtons and the frictional force is only 67 newtons, what's the coefficient of friction? Well, we use the same formula. The frictional force is mu times the normal force. We plug in numbers. I'll plug them in up here. We have the frictional force is 67 newtons, and that's equal to mu, that we don't know, times the normal force, which we do know is 320 newtons. Therefore, mu is 67 newtons over 320 newtons. We pull out our calculator, we divide them, and we see that mu is 0.21. And you'll notice newtons cancels newtons, and 0.21 is our full answer. There are no units in this answer. That's it. Okay, scrolling down. Another force that you should be aware of is called the tension force, or just tension. We abbreviate this as F sub T. In a lot of textbooks, you'll just see it as capital T. We're going to use F sub T because just to remind you, it's another force. So this is a force in a taut cord or rope or string or cable or wire or rod, anything that's long and thin that has a force along it is a tension force. And the interesting thing about tension force, you might say, well, what's the direction? We learned that weight force is always straight down to the center of the earth. Normal force is always perpendicular up from the surface. And frictional force is always the opposite direction of the movement or or attempted movement? Well, tension is always along the length of the rope or the cord or the cable or the wire. And you might say, well, which direction? The answer is both directions, everywhere. So if you imagine some kind of taut rope, and it has to be pulled tight, okay? It can't be just a loose rope. A pulled tight rope or wire or cable or rod or whatever, there's going to be a tension force on it, and it is exact same tension everywhere in both directions at the same time. So if I ask myself, what's the tension here? Well, there's one there and one there. It's always pointing with two arrows, always in the opposite direction, everywhere along that cable. Every point in space has a tension on it. But if somebody said, what's the tension on it? You would just say one of those numbers. You don't add a bunch of numbers up or cancel each other out because they're in the opposite direction. You just say, if each of these F sub t's was 100 newtons, you would just say the tension in the rope is 100 newtons. Simple as that. And the interesting thing is, because it's the same everywhere, let's say you had a tug of war between one team and another team, and let's say this team was giant, okay, and they were all NFL football players, and these people were jockeys who were really small-bodied people and not nearly as strong as these NFL people. Well, and if they pull that rope tight, believe it or not, the tension is identical everywhere along the way, everywhere. Because if the tension is in one direction, there's an equal and opposite tension in the other direction everywhere it is. So the tension in the rope is the same everywhere, no matter whether one side is stronger than the other. I know that's a bizarre concept. All right. And what's interesting about that is when you start studying pulleys, and we're never going to give you something this complex, but when you study pulleys, if you know the tension here, and you might say, well, how do I know the tension? Well, you can literally get one of those spring scales that fishermen use to weigh their fish and put it there. It has all these marks on it. And you could just weigh it, and let's say it comes out and it says 50 newtons on this scale. Well, that's the tension pointing in this direction at that point. It means, because this is all the same rope everywhere along this run, it's 50 newtons of tension everywhere along the same rope. As long as it's the same rope or cable or wire, and they're all connected in one taut line, doesn't matter what the shape is, the tension will be identical everywhere. So we don't have a single formula for tension. It's going to vary, but it is the force along the length of that long, thin object. All right, and the last force I wanted to talk about is not really a specific force. I realize it's in this category of specific forces. It's a type of force, but we just categorize it as applied force, and we abbreviate it as F sub APP for applied, okay? The reason why it's not a specific type of force is this is just a push or a pull of an object by you or an animal or a machine or something that's pushing or pulling some object. So I've got examples in these drawings here. I have a woman pushing a giant rock. I have 3 children pulling another big slab of rock. And then the last one, I have a young girl pulling a sled at an angle that her dog is sitting on. So these are pushes and pulls that happen in everyday activities, and we don't have a specific name for them. So we just, instead of calling them the force of a push or the force of a pull, we just call it applied forces. So it's the force you're choosing to apply, as opposed to forces that automatically arise because of contact or gravity or certain constraints like friction, etc. So applied forces are usually just applied by a push or pull, and they can be direct by just pushing directly, or if you look at the pictures with the children in it, they're pulling or on objects with the use of a rope or a cable. So they're actually using their force on the rope or cable, and that's creating tension, which is applying a force to the slab of rock or to the dog on the sled. But we're just going to call it applied force. We don't have formulas for that because it's really going to depend. And in most of the problems, we're going to give you, if not all of the problems, we're going to tell you what the applied force is. We're going to say this person is pushing this or pulling this with a force of something, and that is the applied force. You just have to remember to call it the applied force. Okay. So here's a little table that summarizes the forces that we just went over. The columns are force, abbreviation, a quick definition, a formula, if there is a formula, and the direction to keep in mind. So gravitational force or weight, F sub g, it's the force due to gravity on any object that has mass. That could be a solid, a liquid, a gas, even a plasma object. We're mostly going to be giving you solid objects. The formula for weight near the Earth's surface is F sub g just equals the mass times little g. You already know little g, 9.8 meters per second squared. We're going to use the positive version for that and then assign a negative sign when we look at the direction of the force. Well, the direction of weight force is always straight down, okay? Straight down towards the center of the Earth. Looking at the next one, normal force, F sub n. This is a perpendicular force. In other words, it's perpendicular up from any surface that's being pressed on, and it provides the force to prevent the object from penetrating it, from falling through. So this is what keeps you from falling through the floor or your books from falling through a table. And if weight is the only other vertical force and your floor is horizontal, it's really simple. The normal force and the gravitational force are the same, but it's perpendicular up from the surface. So normal forces tend to be positive, whereas gravitational forces tend to be negative. So if you want to be technical, we can just remind ourselves this is actually the negative number and this is the positive number that we're calculating. All right. Frictional forces, F sub F. This is the force a surface provides to resist motion of another object on that surface. So two objects sliding on each other, there's a frictional force that makes it hard for that top object to move on the bottom object. And our formula is the frictional force equals a constant, we call the coefficient of friction, times the normal force. It is always in the opposite direction of motion. That might be to the left, it might be to the right, it might be up, it might be down, it might be diagonal. It all depends on the direction of the motion. So I'm not going to assign it a positive and negative, but usually if the applied force is to the right, the frictional force is to the left. Tension, F sub t, this is a force along the length of a taut, in other words, it's tightened, a tight cord, cable, rope, wire, even a thin rod, okay? We don't have a formula for this, but the force is always along the length of the long, thin object, rope, wire, etc., and it's always in both directions, and it's everywhere along that length. An applied force, this is just the force you deliberately apply, you deliberately impose on an object, generally through pushing or pulling. Sometimes you use a rope to pull, but we're not going to worry about the tension in that case. We'll just consider it an applied force, and it's really going to vary with the push or pull. And you just have to keep track of the direction from clues in the problem itself. All right, so little hints. The units of all forces, the unit of all forces is a Newton, N, capital N, okay? All forces are vectors, so they have to have a direction. When you're drawing your free body diagrams, you might have a force this way, you might have a force this way, you might have a force that way, you might have a force that way. You could have forces this way, and we haven't talked about how to deal with diagonal forces. That's beyond the scope of this course, but I'll tell you what you usually do is use trigonometry to take this force and convert it into the sum of two forces you do know how to use. this one and this one. So the sum of these two forces equals this. You do not need to know how to do that, all right? We don't cover that in this course. I'm just mentioning it to you. Some other forces that you might encounter in this course. Air resistance. This is also called drag. When you fall from an airplane right before you pull the parachute, you have very little drag. You have a little bit of drag. It's the air friction pushing up against you. So air resistance is always air friction that's pushing in the opposite direction that you're falling. Well, you're falling down, so the air resistance is up. If you were in a plane flying forward, the air resistance would be backwards. Okay, so it's just an air friction. We call it air resistance or drag. You'll see more of that later when we get to vertical problems. Air resistance becomes very important once you open your parachute. Parachutes have enormous air resistance because they create an enormous amount of surface area that hits that air and creates giant amounts of air friction. Centripetal force. This is something we briefly mentioned, but you're not responsible for. It's a force that points towards the center anytime you have an object rotating. You might say, what? That doesn't make sense. We'll go over that when it comes time. I don't want to spend a lot of time on it now. Centripetal force is what it's called. You may have heard of something called centrifugal force. This is not the same thing. This is actually a real force. Centrifugal force, you're going to learn, is actually not a real force. It's an apparent force that people feel when they're inside an object that's rotating as opposed to being outside the object that is rotating. Spring force, also called elastic force. This is the force of a spring either compressing or extending. We'll show you that, but again, you just need to understand the source of the force. We're not going to be asking you to calculate anything. Electrostatic force, this is something we cover in much more detail in Unit 4. This is the force between electric charges, a positive and a positive charge, which repel, a negative and a negative charge, which repel, or opposite charges, a positive and a negative, or a negative and a positive, which attract, and we'll go over how to calculate those forces in Unit 4. Now, if we scroll down to the bottom of this page, you see there are other forces, and there are a number of other forces that we do not cover in this course, and here are three of the ones that we do not cover in the course. Magnetic force. This is the attraction or repulsion of magnetic poles, the north and south poles of magnets. And the last two forces listed here are the strong nuclear force and the weak nuclear force. The strong nuclear force is the force that's responsible for holding protons and neutrons together in the atomic nucleus. And the weak nuclear force is actually responsible for certain types of radioactivity, radioactive decays that convert protons to neutrons or neutrons to protons, either in the nucleus or outside of the nucleus. And we'll stop this video here. We'll come back for the rest of the lesson in another video.